keeping track of them?
Hi Math 2 students, this is Ms. Van Vickel, and this is your last video in Tuesday, April 21st series on exponential growth and decay without a percent. And I'm working problem 3, and in problem 3 it says that you have a headache and allergies, so you go home from school and take 1,000 milligrams of acetaminophen. You drink 2 cups of water with the capsules and you lie down. The acetaminophen enters your bloodstream, and immediately your kidneys begin to filter the medication out of your blood. After 4 hours, your kidneys have filtered out about 1/4 of the drug. And it asks you to make a table and do some calculations here. So I started out with the initial value being 0 amount of time since taking the drug. And I knew that the number of milligrams in the body at time 0 was 1,000. But to figure out how much is left in your body, we'll have to decide to do some calculations. And so we need to take that 1,000 and we need to remove 1/4 of the drug, because that's what the problem says your kidneys are doing. So I'm interested not in the amount that your kidneys remove, but in the amount that your kidneys do not remove, the amount that remains in your bloodstream. And if your kidneys take away 1/4, what they're leaving is 3/4. Notice we're going to have decay here because this R value is less than 1. So if I take 1,000 and I multiply that times 3/4 or 0.75, my calculation says I end up with 750 milligrams of acetaminophen in my bloodstream. So after 4 hours, and let's go ahead and fill out this table. After 4 hours, there would be 750 milligrams in my bloodstream. And then I would want to go ahead and do that again for the next 4-hour time period. And I'm going to use 0.75 here. So 750 times 0.75 is equal to 562.5. And I'm going to go ahead and round to 563. So after 8 hours, there's 563 milligrams of acetaminophen running through your bloodstream. And we're going to do that again. Take 563 and multiply that times 0.75. And we get 422. I'm going to round to 422. So after 12 hours, there's 422 milligrams of acetaminophen in your bloodstream. So you'll notice what we're doing here is we're repeatedly multiplying by 0.75 over and over again. So it's a lot easier to create an exponential function to model the situation than it is to fill this table out on and on and on. So what we're going to do is we're going to use our basic function, y equals a times r to the t power. And we're going to notice that 1,000 was the initial value of acetaminophen in our bloodstream, and that our body was filtering out 1/4 of it, but was leaving 3/4 behind. So that's what I want to put in for R. And then I know that I need to put 1/4 T here. Let's talk about why we need to do that. If it takes 4 hours for the acetaminophen to remove 1/4 of the value for your kidneys to take that 1/4 out, then if I need to put 4 in for the number of hours, but I only want to remove one iteration of that. So if I put 4 in here, 1/4 times 4 is 1, and that will be the same thing as multiplying 1,000 times 0.75 to the first power, which is what I want to have happen after a 4-hour time period. If I would put in an 8-hour time period, your kidneys would have removed 1/4 of the acetaminophen twice. So you want to put 8 in here, multiply it by 1/4, and get an exponent of 2. So that's why I chose to phrase the exponent the way I did. In part D, it says use the model to determine how much of the drug will be in your body after 24 hours. So all I need to do is put in 24 for my hours. And you can use 0.75 instead of 3/4. It's whatever makes sense to you. So I put 24 in there, and I notice that that is 6 iterations of my kidneys removing the acetaminophen from my bloodstream. So I want to take 0.75 or 3/4 to the 6th power, and then I want to multiply the result of that times 1,000. And after 24 hours, there would still be 177.9, or let's round to 178. There would still be approximately 178 milligrams of acetaminophen in my bloodstream. So problem E says, use the model to determine how many hours have passed since you took the drug if 300 milligrams is still in your bloodstream. And again, notice they're asking me to solve for t, and t is in my exponent. They're saying, you have 300 milligrams in your bloodstream. You started with 1,000 milligrams in your bloodstream. Your body's removing 1/4 of it every 4 hours. And so we want to find t, or x, right here. The problem is, it's in my exponent, and I don't know any kind of algebra maneuver to get that out of my exponent. So I'm going to use my calculator to solve this. To make my numbers more manageable, I'm going to divide both sides by 1,000 first. So if I multiply the left-hand side by 1,000, divide the left-hand side by 1,000, that's 300 divided by 1,000, which gives me 0.3. So on the left-hand side, I have 0.3, and on the right-hand side, I have 0.75 to the 1/4 times t power, or x power. So I'm going to graph L1 and L2 again, and in L1, I'm going to put 0.3, and in L2, I'm going to put 3 divided by 4, and again, you can use 0.75 to the x divided by 4 power. That's the same thing as saying 1/4 times x. Now I'm going to have to make an educated guess on what my window should be, and take a look at this number right here. This is a small number. It's in between 0 and 1. So I've been using really huge values for my y-min and my y-max. Probably doing something like -5 to +5 will be plenty. And I'm not really sure how many hours it's going to take for me to get to this point, but I don't think it's going to take 240 hours. Let's try 48 and see if that window range will do. Okay, so when I look at my graph, I think I still have too big of a y-min and y-max, because it's very hard for me to see what's going on right here where the graphs intersect. So I'm going to go back and set my y-min at -1 and my y-max at 1, and see if I can't see the point of intersection just a little better. And that seems to have helped things. So we're going to find the intersection of these graphs, second calc intersect. And again, I'm going to hit enter on my two functions. And my calculator tells me that after an x value, or 16 hours, my y value is 0.3. So let's look at what that means. That means t is 16. And that means after 16 hours, I would still have 300 milligrams floating around in my bloodstream. So that's it for video number 4 in Tuesday's exploration of exponential functions with modeling growth and decay without a percent. There is one more problem, and it's problem number 4. And I will include it with tomorrow's videos, with Wednesday's videos. It has everything to do with the half-life. And that can be modeled with exponentials as well.